Alright, this is part 3 of a test on graphing rational functions. Please pause the video and try to do number 4 by yourself. If you've already tried and failed to do number 4, then go ahead and watch the video, but put your pencil down. Don't try to do it along with me. Watch the video, learn how to do it, and then go back and do the whole problem by yourself. Alright, doing it by yourself is the only way to learn. Okay, I apologize for my voice as well, guys. I'm losing my voice due to too much talking and not enough sleep. Alright, let's get started. Alright, let's actually start with the horizontal asymptote, because that's easy to nail. The horizontal asymptote works like this. If the numerator degree is less, y equals 0. If the degrees are equal, leading coefficients. If the numerator degree is greater than the denominator, there is no horizontal asymptote. And that's the situation we're in here. Numerator degree is 2, the denominator has degree 1. So there is no horizontal asymptote. So under horizontal asymptote, we're going to go ahead and put none. Okay, now slant asymptotes happen if the numerator degree is 1 more than the denominator, as long as the denominator doesn't divide in evenly. So there's likely to be a slant asymptote. To know for sure, we have to go ahead and divide and see what happens. So because it's just a simple x minus 2, we can do synthetic division. Alright, in the box we put positive 2, and we've got coefficients 2, negative 3, 1. Alright, bring this down, multiply, add, multiply, and add. Okay, so that gives us, alright, the quotient form of this function would be f of x equals, okay, the 2x and the 1 give us 2x plus 1, and then the remainder gives us plus 3 over x minus 2. Alright, notice for a slant asymptote there has to be a remainder. If there is no remainder, there would be no slant asymptote. But the slant asymptote is just going to come from the pink part here, the non-remainder part of the quotient. So y equals 2x plus 1. Alright, let's go ahead and graph that. To graph y equals 2x plus 1, remember y equals mx plus b. This is the y-intercept, so we'll start at 1. Okay, now this 2 represents a slope, so this is up 2, right 1. So we'll go up 2, right 1 repeatedly. And we'll repeat the process in the other direction. Okay, so these points show us where the slant asymptote is. Let's go ahead and graph it as a dotted line. Alright, so there's my slant asymptote. Alright, I know there will be no holes because x minus 2 is my only factor in the denominator. And that does not get canceled out. I don't have to factor this to see that. I can see that there's a remainder. Alright, if this got canceled out, there'd be no remainder. But normally we would factor the numerator and see if anything canceled out. Okay, if something cancels out, then that would be a hole, but nothing cancels on this problem. So there will be no holes because no factors are canceling out. So we will say none. Alright, that means this x minus 2 will give us a vertical asymptote. If we set this equal to 0, okay, adding 2 to both sides gives us x equals 2. That is my vertical asymptote. Okay, let's go ahead and graph that. Alright, so there's my vertical asymptote. Okay, what's next? Alright, we need the y-intercept. Well, guys, if we want the y-intercept, we let x equal 0. Now, if I let x equal 0, alright, that's going to wipe out all three of these terms. Alright, so these three terms are all gone, because this becomes 0, this becomes 0, and of course that's 0. So that's only going to leave the constants. Okay, so that's negative 1/2. Okay, it's coming from that. So this is the y-intercept, so I'm going to put that as my y value. Okay, the x value of the y-intercept is always going to be 0. Okay, now for the x-intercepts, in general, if I want the x-intercept, I let y equal 0. Okay, which means, you know, setting this is the y that I'm talking about. Let me sort of start over. So in general, it's a matter of letting this be 0. Okay, let this be 0. But the denominator can't be 0. So the only way that this function is going to equal 0 is if the numerator is equal to 0. So basically I'm going to wind up setting the numerator equal to 0. Now, to solve that, it would be useful to factor this. Okay, so let's go ahead and factor. Two x squared can only factor as 2x and x. 1 can only be 1 times 1. Alright, remember, inner plus outer must equal middle. Inner, I have 1x. Outer, I have 2x. I'm trying to get a middle of negative 3x. To do that, I will need a negative 2 and a negative 1. Okay, that means both of these would have to be negative. We have to make sure we're getting a positive 1. We are. Negative times a negative is positive. So this is the correct factorization. Now, if I'm setting this equal to 0, then that means I'm setting each of these equal to 0. Okay, so I'm going 2x minus 1 equals 0, and x minus 1 equals 0. Okay, adding 1 to both sides gives me 2x equals 1. Dividing by 2 gives me x equals 1/2. Okay, over here I'm just adding 1 to both sides and getting x equals 1. Okay, so I let y equal 0 and I got these x values. So these are my x-intercepts at 1/2 and 1. Okay, because those are my x-intercepts, I'm going to let these be my x values. Alright, so there's 2 of them. So I had 1/2 and 1. The y values are automatically 0 because they're the x-intercepts. They're right on the x-axis. Okay, let's go ahead and graph these intercepts. So I have 0 comma negative 1/2. Let's graph that. Alright, so here's 0 and negative 1/2, down halfway. Okay, and then the 2 x-intercepts at 1/2 and 1. Okay, so here's an x-intercept at 1/2, and here's another one at 1. Okay, that's interesting. Okay, let's talk end behavior. Oh, well, I want to do the graph before I talk end behavior. Okay, so it's time to graph more points. Alright, based on the asymptotes that are surrounding here, and I can already see this going up and coming back down, I can tell that this is curving like this. But let's get some additional points going. Specifically, I'd like to see what's happening at 1.5. Okay, so some additional points. So I definitely want to see what's happening at 1.5. To play around with all these values and get some values going, I need to put the function in my calculator. So I'm just going to type the function in my calculator. Alright, so here's the now let's keep an eye on the vertical asymptote. We have vertical asymptote at 2. We already have a few values on the left, so let's start off getting a few values on the right. So let's look at like 3, 4, 5, and see what's going on. Okay, so I'm going to start at 3. Okay, so at 3 I'm at 10. Okay, so that's right there. Alright, what about 4? Okay, at 4 I'm at this 21 over 2. If I hit toggle, see that's 10.5. Okay, so it's a little higher. Alright, this is a little bit above 10. So I see what's going on over there. And you know this asymptote goes forever. Maybe let me go ahead and extend this a little bit. Try to not mess it up too bad from where it was. Okay, and same with this one. If I can just extend this out longer. Okay, because it's going off the grid here a little bit. Let me move this too. It's a little bit of a... Okay, I'm cheating and putting a little bit of an extension onto the end of this so you can really see what's happening. But you will just have to fake it as best you can, even though it's off the graph. Just do your best. Okay, now let's go ahead and look at a couple more. So at 5, we're at 12. Okay, so this is 4, so at 5, we'll be here at 12. Alright, and now I would like to see what's happening at 2.5. So let's go back to the table, hit enter. Let's go ahead and type in 2.5 and take a look. Alright, at 2.5 we're also at 12. Okay, so this is 2.5, that's 11, this is 12. Okay, so that gives us a really good idea of what's going on in this area. So in fact, let's go ahead and draw this branch. Alright, so that branch will be looking something like that. Okay, now let's take a look at this branch. I'd really like to know what's happening at 1.5. Okay, I always like to look at the 0.5s on either side of the asymptote. So 1.5 would be a good one. Alright, now I've already got the 0.5s happening, so I can just scroll back now. And wait, I said 1.5, didn't I? So at 1.5 we're at -2. Okay, so at 1.5 we're at -2. Okay, so that really gives me a good idea. Let's go ahead and look at -0.5 though. At -0.5 we are here, and this is -1.2. So at -0.5 we have -1.2, which is about right here. Okay, so that gives me a really good idea of what's going on here. Alright, so and I guess I should be recording some of these values. So for example, all the points I used up here, I'm just going to record those on my table. Okay, so the so the 1.5, that was -2, for example. I'm going to record that, and then I have negative 0.5. Okay, I'm going to just record all these points. So negative 0.5. What was that? That was negative 6/5, and all the rest of it. Alright, so these are all the points I just plotted. Okay, so just record all that on your table. Anyway, we have enough information to go ahead and draw this branch as well. Okay, it looks something like that. Alright. Okay, so the graph viewed as a whole is going to look something like this. Now let's go ahead and knock out that end behavior. As we go to the left, okay, we're looking at this part of the graph, it is going down forever. So that's why we'll have a negative infinity. Okay, now as we go to the right, okay, and this is the right end, it's going up. So that'll be positive infinity. Alright, this middle part has nothing to do with the end behavior, only the far right and the far left. Alright, that's it for problem number 4. Let's take a quick look at number 5 and 6 before we end this video. What type of discontinuity is x equals 2 above? So remember, x equals 2 was a asymptote, vertical asymptote. We talked about 3 different kinds of discontinuity. By the way, a discontinuity is any kind of a break in the function. We talked about infinite discontinuities, that's your asymptotes, jump discontinuities, and point discontinuities, that's your hole. Only one of those is removable. Alright, a point discontinuity is considered removable. The other 2 are non-removable. Alright, so asymptotes are non-removable discontinuities. So x equals 2 is an asymptote, so that's why it is non-removable. Okay, now let's take a look at number 6 where we have to sketch our own. Okay, a graph, alright, meaning one graph, a single graph that has removable and non-removable, should say a, that has a removable and a non-removable discontinuity. Okay, so a removable discontinuity, remember, is a hole. And a non-removable discontinuity, we could make one that had a jump in it, but if we make it like we have been doing them, a non-removable would be like an asymptote. Okay, so I could easily sketch such a graph as that. Let's say this is my x and y axis. Alright, so this is my x-axis, here's my y-axis. Now here comes my graph. Okay, let's see. Let's put some asymptotes in here. So I can have like a horizontal asymptote, let's say, and I'm going to throw a vertical asymptote in here as well. Okay, so far there's my non-removable asymptotes. I mean non-removable discontinuities. Okay, so I just need to put a hole in here somewhere. So I'll just throw a hole in like here. Okay, so if I could have a graph doing something like this. Okay, so there's a removable discontinuity as well as my asymptotes, which are non-removable. So something like that. So just looking for an asymptote and a hole. Alright, that's going to be enough for this video. We will pick up from here with problem number 7, where we have to actually go ahead and do another graph. So it'll be similar to what we just did, but maybe it'll have some other things going on. Okay, and if we have time, we will I'll probably include number 8 in that video as well, depending on how long it takes. Alright, I will see you on the next video.